May 8, 1945. The Burmese jungle near Rangoon lay silent in the pre-dawn darkness, broken only by the distant rumble of approaching aircraft. Inside the massive concrete bunker complex at Elephant Point, Japanese naval commander Takeshi Yamamoto stood beneath 12 feet of reinforced concrete, surrounded by walls designed to withstand anything the Allies could throw at them. His engineers had calculated every angle, every stress point, every potential weakness. The structure had taken 8 months to build, consumed thousands of tons of concrete and steel, and represented the pinnacle of Japanese military engineering in Southeast Asia. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Commander Yamamoto did not know, what Japanese military intelligence had failed to comprehend, was that 6 Lancaster bombers of the Royal Air Force's 6th Squadron were crossing the Bay of Bengal at that very moment, each carrying a single weapon that would rewrite the mathematics of fortification warfare. A weapon so revolutionary that its creator, Barnes Wallis, had been told his idea was impossible. A 12,000-pound bomb designed not to explode on impact, but to penetrate deep into the earth before detonating, creating seismic shockwaves that would collapse structures from within. The Japanese had never encountered anything like the Tallboy, and in the coming weeks, their confidence in concrete would shatter as completely as the bunkers themselves. The story of how a British engineer's obsession with earthquake bombs came to terrorize Japanese defenders begins not in the jungles of Burma, but in the drawing rooms and testing facilities of wartime Britain, where Barnes Wallis wrestled with a problem that had consumed him since 1939. Traditional bombs, no matter how large, dissipated most of their energy at the surface. A 500-pound bomb might create an impressive crater and devastating blast effects against exposed targets, but against hardened structures like submarine pens, railway viaducts, or deeply buried command bunkers, conventional explosives proved frustratingly ineffective. The blast wave expanded outward in all directions, with most of the energy wasted into the atmosphere rather than directed against the target. Wallis, an aircraft designer and engineer at Vickers Armstrong, who had already revolutionized aircraft construction with his geodetic airframe designs, approached the problem from first principles. What if, instead of trying to destroy a target with blast effects, a bomb could be designed to penetrate deep into the earth beside or beneath a structure and then detonate? The explosion, confined by the surrounding earth or concrete, would create a camouflet, a massive underground cavity, and generate seismic shockwaves that would propagate through the ground itself. These shockwaves, Wallis theorized, would be far more destructive to buried or heavily protected structures than any surface explosion could achieve. The physics were sound, but the engineering challenges were immense. To penetrate deeply enough to be effective, a bomb would need to strike the ground at extremely high velocity. This meant dropping from high altitude to allow gravity to accelerate the weapon to terminal velocity. But high-altitude bombing in 1940 reduced accuracy dramatically, and a weapon that missed its target by even a few dozen yards would be completely ineffective. The bomb would also need to be extraordinarily strong to survive the massive deceleration forces of ground impact without shattering, and it would need to be heavy enough that air resistance would not slow it excessively during its fall. Wallis calculated that a truly effective earthquake bomb would need to weigh at least 10,000 pounds, preferably more. In 1940, when the Royal Air Force was struggling to deliver even 2,000-pound bombs to German targets, this seemed fantastical. Wallis persisted despite official skepticism that bordered on dismissal. He wrote papers, conducted small-scale experiments, and pestered anyone in authority who would listen. The Air Ministry remained unconvinced. Britain was fighting for survival. Factories were struggling to produce enough conventional weapons, and resources could not be diverted to experimental projects based on unproven theories. Wallis's earthquake bomb concept languished in bureaucratic limbo through 1940 and 41, while the war ground on and German fortifications grew ever more formidable. The turning point came with the recognition that Germany was constructing massive concrete U-boat pens along the French Atlantic coast, to structures with roofs up to 16 feet thick that could withstand direct hits from the heaviest bombs then available. Conventional bombing raids against these pens achieved nothing beyond expending bombs and risking aircrews. If Britain could not find a way to destroy these facilities, German submarines would continue ravaging Atlantic convoys from invulnerable bases. In February 1942, the Air Ministry finally authorized Wallis to proceed with development of his earthquake bomb concept. The timeline was brutally compressed. Wallis would need to design the weapon, develop specialized manufacturing techniques for its unique casing, create fusing mechanisms that could survive ground impact at hundreds of miles per hour, and identify an aircraft capable of carrying such a massive weapon to target. The engineering challenges multiplied with each requirement. The bomb Wallis designed, initially designated the medium-capacity bomb and later immortalized as the Tallboy, represented a revolutionary departure from conventional ordnance. It measured 21 feet in length and 38 inches in maximum diameter, with a streamlined shape that resembled a massive artillery shell more than a traditional bomb. The casing was manufactured from a single forging of high-grade steel, machined to precise tolerances, and heat-treated to achieve hardness that would allow it to penetrate concrete and earth without fracturing. The weapon contained 5,200 pounds of Torpex explosive, a mixture of RDX, TNT, and aluminum powder that was approximately 50% more powerful than TNT alone. But the Torpex filling represented only 43% of the bomb's total weight of 12,000 pounds. The remaining 7,000 pounds consisted of the immensely strong steel casing designed to survive impact and penetration. This inverted the normal bomb design philosophy, where explosive filling typically represented 70 to 80% of total weight. Wallis was not building a container for explosives. He was building a penetrator that happened to carry explosives deep underground before detonating. The fusing mechanism presented particular challenges. The bomb would strike the Earth at approximately 750 miles per hour after being dropped from 20,000 feet or higher. The deceleration forces during ground penetration would exceed 5,000 times the force of gravity, sufficient to destroy any conventional fuse. Wallis developed a specialized tail fuse with a delay mechanism that would activate only after the bomb had come to rest deep underground, typically 30 seconds after impact. This delay was critical. It allowed the bomb to reach maximum depth before detonating, and it gave the attacking aircraft time to escape the effects of the massive explosion. Early testing of the fusing mechanism required dozens of trials to achieve reliability. Prototype fuses shattered on impact or failed to detonate. Engineers incrementally refined the design, strengthening components, improving the delay mechanism, and testing each modification through actual drops onto specially prepared test ranges. By late 1943, the fusing system had achieved acceptable reliability, though it would never be perfect. Throughout the war, approximately 8% of Tallboys dropped would fail to detonate due to fuse failures, a rate considered acceptable given the extraordinary conditions the fuses endured. The question of delivery aircraft nearly derailed the entire project. No existing Royal Air Force bomber could carry a 12,000-pound bomb. The Lancaster, Britain's most capable heavy bomber, had a maximum bomb load of 14,000 pounds, but its bomb bay dimensions could not accommodate a weapon 21 feet long and 38 inches in diameter. Wallis worked with Avro, the Lancaster's manufacturer, to develop a modified version designated the Lancaster B Mark I Special. This variant had its bomb bay doors removed entirely and replaced with a streamlined fairing that incorporated a trapeze mechanism to carry the Tallboy semi-recessed beneath the fuselage. The dorsal and ventral gun turrets were removed to save weight, and fuel capacity was reduced. Even with these modifications, a Lancaster carrying a Tallboy could not carry a full fuel load and still take off safely. Mission planning for Tallboy operations required careful calculation of target distance, fuel requirements, and acceptable safety margins. The modified Lancasters could reach targets in France and Western Germany with Tallboys, but deeper penetrations into the Reich would require forward staging bases or accepting reduced fuel reserves that left minimal safety margin. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By June 1944, after more than 2 years of development, testing, and modification, the Tallboy was ready for operational use. 6th Squadron, an elite Royal Air Force unit with extensive experience in precision bombing, received the first weapons and began training on the specialized tactics required for effective employment. The crews quickly discovered that delivering Tallboys effectively demanded extraordinary precision. The bombs had to be dropped from at least 18,000 feet to achieve terminal velocity for deep penetration. At this altitude, bomb aiming required accounting for wind drift, air density, temperature variations, and the complex ballistics of a weapon that fell differently than conventional bombs. A Tallboy's streamlined shape gave it unusual aerodynamic properties. It would actually accelerate throughout most of its fall, reaching supersonic velocities in the final seconds before impact, creating a distinctive shrieking sound that survivors would remember long after the war ended. The first operational use of Tallboy bombs occurred on June 8, 1944, when 19 Lancasters of 6th Squadron attacked the Saumur railway tunnel in France. The tunnel, carved through solid rock, carried the main rail line between Paris and Bordeaux and was considered invulnerable to conventional bombing. German military traffic moved through it continuously, supplying forces fighting in Normandy. One Tallboy struck the hillside above the tunnel, penetrated approximately 60 feet into the rock, and detonated. The explosion created a massive camouflet that collapsed the tunnel completely, blocking it with thousands of tons of rock and rendering it unusable for months. The success exceeded even Wallis's optimistic predictions. Reconnaissance photographs showed a crater 100 feet deep and 240 feet wide. The seismic shockwave had shattered rock throughout a vast underground volume, demonstrating conclusively that the earthquake bomb concept worked as theorized. More Tallboy operations followed through the summer and autumn of 1944. The weapons proved devastatingly effective against hardened targets. V-weapon sites, U-boat pens, railway viaducts, and other reinforced structures that had resisted thousands of tons of conventional bombs succumbed to single Tallboy hits. The psychological impact on German defenders was profound. Engineers who had designed structures to withstand anything the Allies could deliver watched their calculations proven worthless as Tallboys punched through concrete that should have been impenetrable. But the war against Germany, while still demanding maximum effort, was clearly moving toward Allied victory by late 1944. The situation in the Pacific and Southeast Asia remained more difficult. Japanese forces, pushed back across Burma by British and Commonwealth armies, had established defensive positions around key transportation hubs and administrative centers. These fortifications, built with Japanese engineering expertise and massive labor inputs, were formidable obstacles. The British 14th Army, fighting its way toward Rangoon, faced bunker complexes and fortified positions that could delay the advance for weeks if they could not be reduced quickly. Japanese military doctrine emphasized defense in depth, with multiple layers of fortifications designed to channel attackers into killing zones. The bunkers themselves were engineering marvels, constructed with reinforced concrete walls often exceeding 8 feet in thickness. The roofs, designed to withstand heavy artillery, ranged from 10 to 15 feet of concrete, reinforced with steel beams and railroad rails. Many were partially buried, with only firing ports and observation slits exposed. Some incorporated multiple chambers connected by tunnels, creating underground complexes that could house hundreds of soldiers with ammunition, food, and water sufficient for extended sieges. Japanese engineers had studied Allied bombing tactics carefully and designed their fortifications accordingly. The structures were positioned to minimize exposure to direct hits, often built into hillsides or concealed beneath jungle canopy. Even when Allied bombers located these positions, conventional bombs proved largely ineffective. 500,000-pound bombs would crater the surrounding earth but leave the bunkers intact. Heavier bombs of 2,000 pounds, dropped with precision, might damage exterior walls, but rarely achieved penetration of the thick concrete roofs. Japanese defenders emerged from bombardments shaken but alive, ready to resume fighting once the bombing stopped. This pattern had repeated throughout the Burma campaign, with British forces expending enormous quantities of bombs and artillery ammunition to reduce fortifications that Japanese troops would simply reoccupy or replace. Commander Yamamoto's bunker complex at Elephant Point represented the culmination of Japanese defensive engineering in Burma. Constructed beginning in October 1944 as British forces advanced south through central Burma, the facility served multiple functions. It housed communications equipment linking Japanese forces, defending Rangoon with units further east. It contained ammunition and supply stockpiles that could sustain defensive operations for months. Most critically, it controlled observation of the approaches to Rangoon from the west, allowing Japanese artillery spotters to direct fire against any British advance along the obvious routes toward the capital. The complex consisted of 7 interconnected bunkers arranged in a rough semicircle, with walls varying from 8 to 12 feet of reinforced concrete, depending on the expected direction of enemy fire. The largest bunker, where Yamamoto maintained his command post, sat partially buried in a hillside with its roof protected by 12 feet of concrete covered by additional earth and vegetation. Japanese engineers had calculated that this thickness could withstand direct hits from British 16-inch naval rifles, the heaviest guns likely to be brought to bear against the position. They had not calculated what would happen if a weapon penetrated deep into the earth beside the structure before detonating. The construction had consumed enormous resources during a period when Japan could ill afford such expenditures. Approximately 3,000 tons of cement had been transported to the site, much of it carried by forced labor through jungle paths after Allied air superiority made road movement suicidal. Steel reinforcement bars, salvaged from demolished buildings in Rangoon and cut from captured British equipment, were laboriously bent and tied into place by work crews that labored around the clock. The concrete itself, mixed on site with aggregate from a nearby river, was poured in continuous operations that sometimes lasted 72 hours to complete critical sections without allowing cold joints that might create structural weaknesses. Japanese Army engineers supervised every phase of construction, consulting detailed manuals and applying lessons learned from defensive operations throughout the Pacific. They had examined photographs of damaged fortifications on other islands, analyzed where structures had failed under American bombardment, and incorporated improvements they believed would make their Burmese bunkers impregnable. Inside the main bunker on the morning of May 8th, Commander Yamamoto reviewed defensive plans with his staff officers. The British advance had accelerated in recent days. Forward observation posts reported enemy units probing toward their positions, testing defenses, identifying strong points. Yamamoto expected a major assault within the week. His garrison of 280 men was well supplied and heavily armed. Machine gun positions covered every approach. Artillery pieces in reinforced emplacements could deliver concentrated fire on any force attempting to advance across the open ground surrounding the complex. The thick concrete walls and roof provided absolute protection against anything short of a direct hit from the heaviest naval guns, and British capital ships were hundreds of miles away. Yamamoto felt confident, his engineers assured him, the bunkers would withstand whatever the enemy could deliver. The defensive position was sound, his men were trained and motivated. If the British wanted Rangoon, they would pay heavily for every yard of advance. What neither Yamamoto nor any member of his staff knew was that British intelligence had identified the Elephant Point complex as a critical target weeks earlier. Reconnaissance aircraft, flying at altitudes that made them invisible and inaudible from the ground, had photographed the position repeatedly. Photo interpreters at headquarters in India had marked every bunker, plotted firing angles, identified ammunition dumps and supply points. The thick concrete construction was obvious in the photographs. Standard bombing would achieve little beyond cratering the surrounding jungle. But 6th Squadron had recently deployed to forward bases in Burma, their specially modified Lancasters loaded with weapons that Japanese intelligence had never reported because Japanese intelligence had no idea such weapons existed. The Tallboys were coming to Southeast Asia, and Japanese confidence in concrete was about to receive a devastating education. The morning of May 8th dawned clear over the Bay of Bengal, visibility unlimited, winds light. Flight Lieutenant John Gingell led the formation of 6 Lancasters, each aircraft carrying a single Tallboy and enough fuel for the mission with minimal reserve. The flight from their forward base to the target would take just under 3 hours at cruising altitude. Jingel's navigator, Flying Officer Robert Chen, had plotted the route carefully to avoid known anti-aircraft concentrations while allowing the formation to reach the target from an approach direction that offered the best bombing geometry. Each Lancaster in the formation carried a crew that had trained extensively on Tallboy operations over Germany. They understood the weapon's requirements and limitations. The bombs had to be dropped from at least 18,000 feet to achieve proper terminal velocity. The approach had to be stable, with minimal turbulence that might throw off the careful aiming calculations. The Mark 14 bomb sight, the most sophisticated available to Bomber Command, still required perfect coordination between pilot and bomb aimer to achieve the accuracy that made Tallboys effective. As the formation crossed the Burmese coast, climbing to bombing altitude, Gingell reflected on the briefing he had received the previous evening. The target was a Japanese command bunker complex, believed to house senior officers coordinating defensive operations around Rangoon. Intelligence assessed the bunkers as heavily reinforced, probably too strong for conventional weapons to damage significantly. The mission called for each Lancaster to drop its Tallboy on a separate aiming point, saturating the target area with 6 of the massive weapons in the span of approximately 3 minutes. The briefing officer had emphasized that even near misses might prove effective. The Tallboy's seismic effect meant that a bomb landing within 50 yards of a bunker could potentially collapse it through ground shock alone, without direct penetration of the structure. Gingell had noted the qualification in that statement. Potentially, the Tallboy had never been used against targets in Southeast Asia. Everything known about its effects came from operations over Europe. Whether it would perform similarly in the different soil conditions and geological structures of Burma remained theoretical. At 18,500 feet, the formation leveled off and began the bombing run. Through breaks in the scattered clouds below, Gingell could see the Burmese landscape spread out like a detailed map. Rivers wound through green jungle, occasional clearings marked villages or agricultural areas, and in the distance, the sprawl of Rangoon was visible through the haze. The navigator's voice came through the intercom, calm and precise, calling course corrections as they approached the initial point where the bombing run would begin. Gingell made minor adjustments to heading and airspeed, holding the Lancaster as steady as possible while his bomb aimer, Sergeant Thomas Wright, peered through the bomb sight and began the final calculations that would determine where 12,000 pounds of high explosive and steel would strike the earth. Far below, inside the main bunker at Elephant Point, the first warning of approaching aircraft came from an observation post on the bunker's roof. The soldier manning the position had heard engines, faint but distinctive, the deep throb of multi-engine bombers at altitude. He reported to the command post, and within seconds, alarms sounded throughout the complex. Men grabbed helmets, checked weapons, and moved to assigned positions. Some crews manned anti-aircraft guns positioned around the perimeter, though they knew from experience that aircraft at high altitude were nearly impossible to hit with the light weapons they possessed. Others simply took cover in the deepest sections of the bunkers and waited. They had endured bombing before. The thick concrete would protect them as it always had. The bombers would expend their loads, crater the surrounding jungle, and depart. Then the garrison would emerge, count the near misses, repair any minor damage, and resume defensive preparations. Commander Yamamoto stood in his command post, listening to reports as lookouts tracked the approaching aircraft. 6 bombers, flying in formation at extreme altitude, were approaching from the west. The altitude suggested British heavy bombers, probably Liberators, or the 4-engine Lancasters that had appeared over Burma in recent months. 6 aircraft meant a relatively small raid, probably a harassment attack rather than a serious attempt to reduce the fortifications. Yamamoto felt a moment of satisfaction. The British were wasting effort and valuable bombs on a target they could not seriously damage. Let them bomb. His bunkers would stand, his men would be safe, and the British would learn that some positions could not be taken from the air. Sergeant Wright, peering through his bomb sight in the lead Lancaster, watched the target complex resolve into clarity as the aircraft approached. The concrete bunkers were clearly visible. Grey rectangles among the green jungle, exactly where the reconnaissance photographs had shown them. He made final adjustments, accounting for wind drift and the aircraft's ground speed, watching the crosshairs track toward the aiming point marked on his plotting board. The Tallboy hung beneath the fuselage, held by the trapeze mechanism that would release it cleanly when Wright pressed the bomb release. At this altitude, with the target still over a minute away at their current speed, the waiting felt interminable. Wright forced himself to breathe steadily, to maintain focus, to ignore the knowledge that 5 other aircraft were following behind him, their bomb aimers making their own calculations, each preparing to drop their massive weapons on slightly different aiming points to ensure coverage of the target area. The crosshairs settled on the aiming point. Wright's finger hovered over the release button. The seconds counted down. 5, 4, 3, 2, 1. He pressed the button. The Lancaster lurched upward, as 12,000 pounds suddenly released from beneath the fuselage. The bomb trapeze mechanism swung empty. Wright immediately began tracking for the next aircraft in the formation, calling corrections over the radio to help guide their drops. Behind and below, the Tallboy fell away into empty air, beginning its journey toward the Earth 18,000 feet below. The bomb's aerodynamic shape gave it unusual flight characteristics. Unlike conventional bombs that tumbled and yawed during descent, the Tallboy remained stable, its fins keeping it aligned with its direction of flight. It accelerated steadily under gravity's pull, the streamlined shape minimizing air resistance. At 10,000 feet, it was traveling at over 400 miles per hour. At 5,000 feet, approaching terminal velocity, it exceeded 550 miles per hour. In the final seconds before impact, as it punched through the denser air near the surface, the distinctive shriek of its passage became audible on the ground, a sound unlike anything most people had ever heard. Inside the bunker complex, the Japanese garrison heard that sound in the final 2 seconds before impact. It started as a distant whistle, rapidly rising in pitch and volume, becoming a scream that seemed to come from everywhere at once. Men looked up instinctively, though the thick concrete above them revealed nothing. The scream rose to an unbearable intensity. Then the first Tallboy struck the earth. It hit 37 feet from the main bunker's western wall, travelling at 723 miles per hour. The impact itself was almost silent, a solid thump that transmitted through the ground rather than the air. The bomb punched through 12 feet of topsoil and clay in a fraction of a second, barely slowing. It hit harder rock beneath and penetrated another 15 feet before the enormous deceleration forces finally brought it to rest. The fuse, designed to withstand exactly this sort of treatment, activated its delay mechanism. 30 seconds began counting down. Commander Yamamoto had just enough time to register that something unusual had occurred. The impact sounded different from conventional bombs. There was no immediate explosion, no blast wave, no shower of dirt and debris. For a moment, confusion reigned in the command post. Had the bomb been a dud? Had it buried itself so deeply that the explosion was muffled? Before anyone could formulate an answer, the fuse completed its delay cycle, and 5,200 pounds of Torpex detonated 27 feet underground. The explosion did not propagate outward in a conventional blast wave. Confined by surrounding earth and rock, the detonation created a massive spherical cavity, approximately 40 feet in diameter. The expanding gases, unable to escape upward quickly due to the overburden of soil and rock, transmitted their energy laterally and downward as a seismic shockwave travelling through the ground at the speed of sound in rock, approximately 11,000 feet per second. This shockwave hit the bunker's foundation in less than 1/100th of a second after detonation. The bunker had been designed to withstand vertical loading from bombs exploding on or near its roof. The 12 feet of reinforced concrete above provided enormous compressive strength. What the structure had not been designed for, what Japanese engineers had not anticipated, was a massive shockwave propagating horizontally through the ground itself, hitting the foundation and lower walls with force equivalent to a localized earthquake measuring over 6 on the Richter scale. The foundation cracked instantly. Stress fractures radiated through the concrete like lightning, propagating at thousands of feet per second. The western wall, already subjected to tremendous lateral force from the ground shock, began to fail. Vertical cracks appeared, widening as the structure's integrity collapsed. The roof, unsupported along one side as the wall beneath it crumbled, sagged and then fell inward in a cascade of breaking concrete and twisted steel reinforcement. The men inside experienced this catastrophe as a chaos of noise, motion, and darkness beyond any nightmare. The initial shockwave threw many off their feet. The sound was not a sound but a physical assault, a pressure wave that stunned eardrums and disrupted balance. Then the structure began coming apart. Chunks of concrete crashed down from the ceiling, walls leaned inward at impossible angles. Dust filled the air so thick it was like being underwater in muddy liquid. Men screamed, though the sound was lost in the greater roar of collapsing concrete. Some were crushed instantly by falling debris. Others found themselves trapped in shrinking pockets of space as the bunker collapsed around them. Commander Yamamoto, standing near the center of the command post when the explosion occurred, survived the initial collapse by pure chance. A heavy wooden table above him caught a falling concrete beam, creating a small cavity in the debris. He lay in absolute darkness, barely able to breathe in the dust-choked air, unable to move his legs, and listened to the sounds of dying men echoing through what remained of his command post. Above ground, the second Tallboy struck 22 seconds after the first, impacting 43 feet from a different bunker in the complex. The same sequence repeated: ground penetration, delay, detonation, seismic shockwave, structural collapse, then the third bomb, the fourth, the fifth, the sixth. In the span of 3 minutes and 47 seconds, 6 Tallboys struck the Elephant Point complex, transforming it from a formidable defensive position. The Lancasters, having completed their bomb runs, turned for home. The crews could see smoke and dust rising from the target area, but from 18,000 feet, detailed damage assessment was impossible. That would require reconnaissance aircraft with cameras to return later and photograph the results. For now, Gingel's formation focused on the long flight back to base, nursing their fuel supplies and hoping no Japanese fighters decided to intercept. Behind them, at Elephant Point, the garrison was destroyed. Some men had died instantly in the collapses. Others lay trapped in small cavities within the rubble, slowly suffocating or bleeding out from injuries. A handful of survivors from outlying positions that had been less thoroughly destroyed began digging frantically, trying to reach trapped comrades. But the sheer volume of broken concrete made rescue almost hopeless. Commander Yamamoto remained conscious in his concrete prison for approximately 3 hours. He could hear nothing except his own breathing and the occasional settling of rubble. His legs were numb, either pinned or crushed. He could not tell in the darkness. His thoughts remained surprisingly clear. He understood what had happened, though he could not comprehend the details. Some new type of weapon had been used against his bunkers, something that could destroy structures his engineers had promised were invulnerable. The confidence he had felt that morning seemed now like the foolishness of a child who believes wishes can alter reality. His bunkers had not withstood the attack. His garrison was dead or dying. The defensive position he had been charged with holding no longer existed as a functional military asset. As consciousness faded, his final thoughts were not of glory or honor, but simple incomprehension at how completely the certainties of his world had been shattered. The reconnaissance aircraft that photographed Elephant Point on the afternoon of May 9th captured images that would be studied intensively by intelligence analysts and bomb damage assessment specialists. The bunker complex had been effectively obliterated. 4 of the 7 major structures were completely collapsed, reduced to rubble piles that barely rose above ground level. 2 others were severely damaged, with walls breached and roofs partially fallen. Only one outlying bunker, beyond the zone where Tallboys had impacted, remained structurally intact, though its garrison had already abandoned it, recognizing that position could not be defended. The craters created by the Tallboy explosions measured approximately 70 to 90 feet in diameter and 30 to 40 feet deep. But these craters told only part of the story. The real destruction occurred underground, in the massive camouflets created by the detonations and the seismic effects that had propagated through the earth, to shatter concrete that should have been impregnable. British intelligence officers examining the reconnaissance photographs understood immediately that they were looking at something significant. The Tallboy had proven equally effective in Southeast Asia as it had been over Europe. More importantly, it had demonstrated the vulnerability of even the most heavily constructed Japanese fortifications to weapons employing the earthquake bomb principle. As British forces prepared for the final assault on Rangoon, planners began identifying other Japanese bunker complexes and fortified positions that might benefit from Tallboy treatment. The weapon's psychological impact promised to be as valuable as its physical destructive power. Japanese troops who witnessed what Tallboys could do to bunkers they had believed indestructible would be far less confident in their defensive positions. That erosion of confidence could affect behavior and tactical decisions in ways that were difficult to quantify but potentially decisive. The broader implications reached beyond immediate tactical applications. Japan had invested enormous resources throughout the Pacific in constructing fortified positions designed to make Allied advances prohibitively costly. Island garrisons sat in bunkers and cave complexes that conventional bombardment could not reduce, forcing American forces to engage in brutal close-quarters combat to eliminate defenders one position at a time. If weapons like the Tallboy could be produced in sufficient quantities and delivered against these fortifications, the calculus of island warfare might shift significantly. Defences that had seemed impenetrable could be collapsed before assault forces even landed. The psychological impact on Japanese defenders, who had been taught that their fortifications would protect them against American firepower, could be devastating to morale and combat effectiveness. These considerations were reaching senior Allied planners even as the first Asalo Salfi, rubble at Elephant Point, was still settling, and survivors were still trying to dig out their buried comrades. The Tallboy's success in Burma immediately raised questions about production and allocation. The weapons were expensive and difficult to manufacture. Each bomb required high-grade steel that was in constant demand for other purposes. The machining process was complex and time-consuming. The Torpex explosive filling, while more powerful than standard TNT, was also more expensive to produce and required specialized handling. Throughout 1944 and into 45, total Tallboy production remained limited by these factors. Approximately 854 Tallboys were manufactured during the war, with production priorities favoring operations in Europe where the weapons could be employed against strategic targets like U-boat pens, railway viaducts, and V-weapon sites. The decision to allocate Tallboys to Southeast Asia represented a significant commitment of scarce resources, justified by the potential to accelerate the campaign and reduce Allied casualties. The news of Elephant Point's destruction spread through Japanese military channels with the speed of rumor and the weight of catastrophe. Within 48 hours of the attack, garrison commanders throughout Burma and the broader Southeast Asian theater were receiving fragmentary reports that contradicted everything they had been told about the security of their fortified positions. The initial accounts seemed almost fantastical. A handful of British bombers had destroyed one of the most heavily fortified positions in the theatre using some type of new superbomb that could collapse bunkers from underground. Japanese intelligence officers, already struggling with incomplete information and the fog of a losing war, attempted to separate fact from panic-driven exaggeration. But the reconnaissance photographs, captured by British aircraft and later obtained through various intelligence channels, told a story that could not be dismissed. The bunker complex at Elephant Point had been reduced to rubble by a bombing attack that had involved only 6 aircraft. Lieutenant Hiroshi Tanaka commanded a garrison of 190 men defending a fortified position near Pegu, approximately 50 miles north of Rangoon. His bunkers, constructed over 6 months with forced labor and scarce materials, were smaller than those at Elephant Point, but built to similar specifications. Walls 8 feet thick, roofs 10 feet of reinforced concrete, firing positions designed to cover the approaches to a critical railway bridge. When reports of Elephant Point reached Tanaka on May 10th, he immediately convened his engineering officer to review their own fortifications. Captain Kenji Matsumoto, who had supervised the construction, assured Tanaka that their position was sound. The concrete had been properly mixed and poured, the steel reinforcement was adequate, and the overhead cover would protect against anything except direct hits from the heaviest naval guns. Tanaka wanted to believe these assurances, but the photographs he had been shown told a different story. If British bombers possessed weapons capable of collapsing 12-foot-thick concrete bunkers at Elephant Point, what made Matsumoto think their own positions would fare any better? This conversation, repeated in dozens of Japanese command posts throughout Burma and beyond, represented a fundamental psychological shift. For years, Japanese military doctrine had emphasized the defensive value of fortified positions. Troops who could not retreat, who were expected to fight to the last man, found psychological comfort in thick concrete walls that seemed to promise protection even when surrounded and outnumbered. The bunkers were not merely military assets, but symbols of security in an increasingly desperate strategic situation. Now that security was revealed as illusory, if the British could destroy the strongest bunkers with half a dozen aircraft, then every fortified position in the theatre was potentially vulnerable. This realization affected planning, morale, and the willingness of troops to remain in positions where they might be buried alive by weapons against which there was no defense. The British understanding of Tallboy's psychological impact developed more slowly, but proved equally significant for operational planning. Squadron leader James Bazin, who had led several Tallboy missions over Germany before deploying to Burma, discussed the weapon's effects with intelligence officers at a debriefing following the Elephant Point raid. Bazin noted that the Germans had responded to Tallboy attacks by abandoning certain types of fortified positions and dispersing critical facilities that might be targeted. V-weapon sites that had been concentrated in heavily protected bunkers were moved to more dispersed locations after Tallboys demonstrated the ability to collapse the protective structures. U-boat operations shifted away from the massive concrete pens after repeated Tallboy attacks made those facilities unusable. The weapons created fear disproportionate to the actual number employed, because defenders could never be certain which positions would be targeted next. Bazin believed similar effects might occur in Southeast Asia, as Japanese forces realized their bunkers provided no absolute protection. British operational planners immediately recognized the implications. Major General Thomas Hutton, coordinating air operations in support of the advance on Rangoon, requested additional Tallboy allocations for targets throughout the theatre. His staff had identified 17 major Japanese bunker complexes and fortified positions between their current front lines and Rangoon. Conventional bombing and artillery had already been employed against several of these with minimal results. The Japanese simply absorbed the bombardment in their bunkers and emerged to fight once the shelling stopped. But if Tallboys could be employed against even a fraction of these positions, the demonstration effect might convince Japanese commanders that bunker defense was futile. Troops who believed their positions could be collapsed at any moment would be more likely to withdraw or surrender, rather than fighting prolonged defensive actions that could delay the British advance for weeks. The allocation of Tallboys remained constrained by production and logistical realities. The Royal Air Force had only a limited number of the weapons available, and competing priorities in Europe still demanded the majority of production. The modified Lancasters capable of carrying Tallboys were equally scarce, with most committed to operations against remaining German strategic targets. Nevertheless, the demonstrated effectiveness at Elephant Point convinced higher command to allocate additional resources to Southeast Asia. By mid-May 1945, 6th Squadron had received authorization for 3 additional Tallboy missions against Japanese targets in Burma, with the possibility of more if results justified the expenditure. Each mission would involve between 4 and 8 aircraft, each carrying a single Tallboy, targeting fortified positions that British intelligence assessed as critical to Japanese defensive plans. The second Tallboy mission in Burma occurred on May 15th, targeting the bunker complex near Pegu that Lieutenant Tanaka defended. British reconnaissance had identified this position weeks earlier as a key node in Japanese defences. The bunkers controlled observation over a railway bridge that British forces would need to advance supplies toward Rangoon. Conventional attacks had failed to reduce the position significantly. Artillery bombardment cratered the surrounding area but left the bunkers intact. Fighter-bomber attacks with rockets and cannon fire achieved minor damage but could not penetrate the thick concrete. Tanaka's garrison had grown confident that their position was too strong to be taken except by costly ground assault. The arrival of Tallboys would shatter that confidence in approximately 4 minutes. Flight Lieutenant David Cooper led the formation of 5 Lancasters approaching Pegu at 18,000 feet on the morning of May 15th. The weather was excellent, visibility unlimited, winds moderate. Cooper's bomb aimer had studied reconnaissance photographs of the target until he could visualize every bunker, every firing position, every detail of the complex. The aiming points had been carefully selected to distribute the 5 Tallboys across the target area, maximizing the probability that at least some would achieve direct hits or near misses close enough for the seismic effects to collapse the bunkers. As the formation approached the initial point for the bombing run, Cooper made minor adjustments to heading and airspeed, settling the Lancaster into the stable flight path that would give his bomb aimer the best possible conditions for accurate delivery. Inside the main bunker at Pegu, Lieutenant Tanaka received warning of approaching aircraft at 8:47 in the morning. His lookouts reported multiple bombers at extreme altitude, approaching from the southwest. Tanaka ordered his men to battle stations, then retreated to the deepest section of his command bunker. He had spent the previous 5 days thinking about Elephant Point, about those photographs of collapsed concrete and the reports of entire garrisons buried alive. His engineering officer's assurances seemed hollow now. If those bunkers could be destroyed, so could his. But there was nothing to do except take cover and hope. Hope that the British were attacking some other target nearby. Hope that if bombs did fall on his position, they would be conventional weapons his bunkers could withstand. Hope that the war would end before the new super bombs reached every fortified position in Burma. The first Tallboy released from Cooper's Lancaster at 8:51. The weapon fell away cleanly, beginning its supersonic descent toward the earth nearly 4 miles below. The bomb aimer in the second Lancaster watched the release, counted seconds, then dropped his own weapon. The third, fourth, and fifth Tallboys followed at carefully calculated intervals, designed to ensure all 5 bombs would impact within a 90-second window. As the weapons fell, the Lancaster crews could do nothing but maintain their flight paths and wait for the bombs to reach their targets. From 18,000 feet, watching a Tallboy impact was nearly impossible. The weapons were too small and falling too fast to track visually. Only the subsequent explosions, marked by rising columns of smoke and dust, would confirm that the weapons had detonated successfully. The distinctive shriek of the first Tallboy's passage reached the Japanese garrison approximately 2 seconds before impact. Men who had never heard that sound before looked up in confusion and growing terror. Veterans of Elephant Point, the handful who had survived and been reassigned to other positions, recognized it immediately and threw themselves to the ground, knowing it would make no difference but unable to stop the instinctive reaction. The bomb struck 31 feet from the northeastern corner of the main bunker, penetrated through 24 feet of earth and softer rock, and detonated. The seismic shockwave propagated through the ground at thousands of feet per second, hitting the bunker's foundation with devastating force. Stress cracks radiated through the concrete. The northeastern wall began to fail, bowing inward as its structural integrity collapsed. The roof sagged as support from beneath disappeared. Then, the second Tallboy detonated 47 feet from the western side of the complex, and the cumulative seismic effects from both explosions caused catastrophic structural failure throughout the position. Lieutenant Tanaka experienced the collapse as a sequence of sensations that his mind struggled to process. The initial shockwave threw him against the bunker wall with enough force to crack ribs. Before he could recover, the ceiling above him began coming down. A concrete beam, reinforced with steel rods as thick as a man's wrist, crashed down 3 feet to his left. Dust filled the air instantly, so thick he could not see his own hands. The roaring sound of collapse seemed to go on forever, though in reality the major structural failure occurred in less than 15 seconds. When the noise finally diminished to the settling of rubble and the groans of twisted steel, Tanaka found himself pinned beneath debris in total darkness, unable to move his lower body, struggling to breathe in the dust-choked air. Around him, he could hear screams, some cut off abruptly, others continuing until they weakened and fell silent. Of his 190 men, approximately 37 would survive the attack, mostly those who had been in outlying positions or above ground when the Tallboys struck. The rest died in the collapse or from injuries sustained when the bunkers came down on top of them. The third, 4th, and 5th Tallboys struck other bunkers in the complex, repeating the pattern of penetration, delayed detonation, and seismic destruction. By the time the last weapon exploded, the Pegu fortified position had ceased to exist as a functional military installation. British reconnaissance aircraft photographing the site that afternoon found a rubble field similar to what had been created at Elephant Point. The bunkers that Japanese engineers had calculated could withstand anything the Allies could deliver had been reduced to broken concrete and twisted steel in less than 2 minutes of actual bombing. The psychological impact of this second demonstration of Tallboy effectiveness spread even more rapidly than news of Elephant Point had. Now, Japanese commanders throughout the theatre understood they were facing not a one-time weapon employment, but a systematic capability that could be applied against any fortified position the British chose to target. Major Yoshio Nakamura commanded defences at a bunker complex southeast of Rangoon that British intelligence had not yet identified as a high-priority target. When reports of both Elephant Point and Pegu reached him on May 16th, Nakamura faced a decision that would have been unthinkable weeks earlier. His orders were explicit: hold the position, defend to the last man, allow no British advance through his sector. But those orders had been written before the superbombs appeared. Nakamura's bunkers, while substantial, were not significantly stronger than those that had been destroyed at Elephant Point and Pegu. If British bombers decided to target his position, his entire garrison would be buried alive in collapsed concrete, dying without ever seeing the enemy, unable to fight back or retreat. The prospect was intolerable. After consulting with his senior officers, Nakamura made a decision that reflected the psychological impact Tallboys were having on Japanese defensive doctrine. He ordered his garrison to abandon the bunkers and establish defensive positions in the surrounding jungle, where they would be vulnerable to artillery and air attack, but at least would not be trapped underground when the superbombs fell. This abandonment of fortified positions, repeated by several Japanese commanders in the weeks following the Tallboy demonstrations, represented exactly the psychological effect British planners had hoped to achieve. The weapons were forcing Japanese troops out of their strongest defensive positions through fear alone, without the British needing to employ Tallboys against every fortified complex in the theatre. The mere possibility that Tallboys might be used was sufficient to make bunker defence seem suicidal rather than secure. This shift in Japanese tactical thinking accelerated the British advance significantly. Positions that might have required days or weeks of bombardment and costly ground assault to reduce were being abandoned as Japanese forces withdrew from fortifications they no longer trusted to protect them. The technical characteristics of Tallboy operations in Southeast Asia revealed both the weapon's capabilities and its limitations under tropical conditions. The bombs performed fundamentally the same in Burmese soil as they had in European targets, but the different geological and environmental conditions created some variations in effects. The soil in much of Burma consisted of layers of clay, sand, and softer rock that allowed deep penetration. Tallboys regularly penetrated 25 to 30 feet before detonating, creating massive underground cavities and seismic effects that propagated efficiently through the relatively uniform soil structures. However, the tropical climate created challenges for the attacking aircraft. High temperatures and humidity at lower altitudes created turbulence that could affect bombing accuracy. Monsoon weather patterns limited operational windows, with heavy rain and low clouds making high-altitude precision bombing impossible during certain periods. The forward bases from which 6th Squadron operated had limited facilities compared to bases in Britain, complicating maintenance of the specialised Lancaster variants and the delicate Tallboy fusing mechanisms. Squadron leader Bazin noted in his operational reports that Tallboy missions in Burma required even more careful planning than similar missions over Europe. The longer distances from base to target meant fuel calculations had to be precise, with minimal margin for error. Navigation over featureless jungle terrain was more difficult than over European landscapes with their distinctive cities, rivers, and roads. Target identification from 18,000 feet could be challenging when bunkers were concealed beneath jungle, a canopy, or camouflage. Several missions had to be aborted when cloud cover obscured targets, or when navigation errors meant the formation was not positioned correctly for the bombing run. These operational challenges reduced the overall effectiveness of Tallboy employment in Southeast Asia compared to Europe, though when missions did achieve successful weapon delivery, the results were consistently devastating. The question of whether Tallboys could be employed against Japanese fortifications in the broader Pacific theater generated significant discussion among Allied planners in mid to late 1945. The success in Burma demonstrated the weapon's effectiveness against bunker complexes, but the logistical challenges of employing them across the vast distances of the Pacific seemed almost insurmountable. The modified Lancasters required bases with adequate runways, maintenance facilities, and specialized handling equipment for the massive bombs. They needed fuel supplies sufficient for missions that might involve thousands of miles of overwater flight. Most critically, they needed forward bases close enough to targets that the aircraft could reach them with acceptable fuel reserves. In the European theater, Britain provided a secure base from which bombers could reach targets throughout Germany and occupied Europe. In the Pacific, every island had to be captured and developed before it could serve as an airbase, and even then, many targets remained beyond reach of Britain-based aircraft. American planners examining the Tallboys' success developed their own interest in similar weapons. The United States had been developing a comparable deep-penetration bomb, eventually designated the Disney, though development had proceeded more slowly than the British program. The Disney bomb, when it finally entered production in limited numbers in late 1945, incorporated similar principles to the Tallboy, but with some design differences reflecting American manufacturing capabilities and operational requirements. At approximately 4,500 pounds, the Disney was lighter than the Tallboy, sacrificing some penetrating power for the ability to be carried by a wider range of aircraft. American planners envisioned employing Disney bombs against Japanese fortifications on islands like Iwo Jima and Okinawa, where bunker complexes had proven extraordinarily difficult to reduce with conventional weapons. However, the timeline of the war's conclusion meant these plans never advanced beyond initial stages. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945, combined with Soviet entry into the Pacific War, forced Japan's surrender before deep penetration bombs could be employed systematically against island fortifications. The survivors of Tallboy attacks in Burma carried physical and psychological scars that shaped their understanding of modern warfare for the rest of their lives. Lieutenant Tanaka, pulled from the rubble at Pegu 47 hours after the attack with crushed legs and internal injuries, spent 3 months in a field hospital before being evacuated to Japan after the surrender. In post-war interviews, he described the experience of being buried alive as the most terrifying of his wartime service, worse than combat, worse than bombardment, worse than the hunger and disease that plagued Japanese forces in the final months. The helplessness of being trapped underground, unable to move, unable to see, slowly suffocating while listening to other men die around him, created trauma that persisted for decades. He noted that the bunkers Japanese engineers had promised were invincible, proved worthless against weapons that attacked from underground rather than above. The confidence soldiers felt in fortified positions was revealed as false security, a psychological comfort that could be shattered by weapons designed specifically to exploit the vulnerabilities those positions concealed. The British crews who delivered Tallboys against Japanese targets in Burma had mixed feelings about the weapon's effects. On one level, they recognized that successfully reducing fortified positions saved Allied lives by making ground assaults less costly or unnecessary. Bunkers that might have required days of fighting to capture could be collapsed in minutes, eliminating Japanese defensive capabilities without exposing British and Commonwealth troops to direct fire. The Tallboy missions were also professionally satisfying for bomber crews who had spent years attacking targets with weapons of uncertain effectiveness. The dramatic, unambiguous results of Tallboy strikes provided validation that their efforts were achieving concrete military objectives. But some crew members expressed discomfort with the nature of the weapon's effects. Burying enemy soldiers alive in collapsed bunkers seemed particularly brutal, even in the context of a war that had featured countless atrocities. Flight Sergeant Michael Harrison, a bomb aimer who participated in 3 Tallboy missions over Burma, later wrote that he understood intellectually why the weapons were necessary, but could not entirely suppress unease about what happened to the men inside those bunkers when the bombs detonated. The technical lessons learned from Tallboy employment in Southeast Asia influenced post-war bomb design and delivery tactics. British ordnance engineers analysing mission reports and damage assessment photographs refined their understanding of how deep penetration weapons performed under various soil conditions. The data collected from Burma operations contributed to improved models for predicting weapon effects, calculating optimal aiming points, and determining how many bombs would be required against different types of fortified structures. These technical insights fed into Cold War-era developments of bunker-busting weapons designed to attack hardened Soviet command facilities and missile silos. The underlying principle remained constant across decades. Weapons that could penetrate deeply before detonating, creating underground shock effects, were far more effective against buried or heavily protected targets than surface explosions of any magnitude. Modern bunker-busting munitions, including the American GBU series of guided penetrating bombs, represent direct descendants of the concepts Barnes-Wallis pioneered with the Tallboy. The broader strategic impact of Tallboy operations in Burma was difficult to quantify precisely but clearly significant. British forces captured Rangoon on May 3, 1945, earlier than some planning estimates had predicted. While multiple factors contributed to the speed of the advance, the psychological impact of Tallboy attacks on Japanese defensive preparations played a measurable role. Fortified positions that should have been defended tenaciously were abandoned or surrendered after minimal resistance. Japanese commanders who had been ordered to hold specific bunker complexes found their garrisons unwilling to remain in positions that might be collapsed by superbombs at any moment. The erosion of confidence in fortified defense forced Japanese forces into less favorable tactical situations where British advantages in artillery, air support, and logistics could be brought to bear more effectively. The few Tallboy missions actually flown in Burma achieved effects disproportionate to the number of weapons employed because the threat of future Tallboy attacks influenced Japanese decision-making throughout the theatre. Commander Yamamoto died in the rubble of his command post at Elephant Point sometime on the afternoon of May 8, 1945. His body was recovered 3 weeks later by Japanese work parties clearing the site under British supervision. He was 41 years old and had served in the Imperial Japanese Navy for 19 years. His family in Osaka received notification of his death in July, after Japan's surrender. The official report stated he had died defending his position against enemy attack. It did not mention that he and most of his garrison had been buried alive when weapons they had never heard of, collapsed bunkers their engineers had promised were impregnable. His widow, Akiko, raised their 3 children in post-war Japan, telling them their father had died honorably in service to his country. She never learned the specific details of how he died, and perhaps that was merciful. The reality of being slowly crushed and suffocated in collapsed concrete in absolute darkness was not something families needed to know. Barnes-Wallis learned of the Tallboy's success against Japanese targets in Burma through official channels in late May 1945. By then, he was already working on an even larger weapon, the Grand Slam, which weighed 22,000 pounds and represented an evolution of the earthquake bomb concept to its logical extreme. The Grand Slam would see limited use against German targets in the final months of the European War, but would never be employed against Japanese fortifications. Wallis's reaction to the Burma operations was characteristically focused on technical details rather than broader implications. His correspondence from this period discusses penetration depths achieved in different soil types, the effectiveness of the seismic shockwave against various concrete thicknesses, and potential improvements to fusing mechanisms. The human cost of the weapons he had designed, the men buried in collapsed bunkers or crippled by the structural failures his bombs created, rarely appeared in his technical writings. This was not callousness, but rather the compartmentalization necessary for engineers working on weapons of war. Wallis had designed the Tallboy to solve a specific military problem, destroying hardened targets that conventional weapons could not damage. That it solved this problem by creating underground cavities that collapsed fortifications and buried their occupants alive was a technical consequence of the weapon's operating principles, not a moral consideration that affected its development or employment. The final Tallboy mission against Japanese targets in Southeast Asia occurred on June 9, 1945, targeting a bunker complex in southern Burma that had been identified as a headquarters for Japanese forces still resisting British control of the region. By this point in the war, organized Japanese resistance in Burma had largely collapsed. Rangoon had fallen, major units had surrendered or been destroyed, and remaining Japanese forces were fragmented and cut off from supply. The mission proceeded despite questions about whether the target justified the expenditure of precious Tallboys against a defeated enemy. 4 Lancasters delivered their weapons successfully, collapsing the bunker complex and killing approximately 130 Japanese soldiers who had been using it as a refuge while attempting to evade capture. Post-war analysis questioned whether this mission had been necessary or simply a demonstration of capability against an enemy that no longer posed significant threat. The debate reflected broader questions about the employment of overwhelming force in warfare's final stages, when victory is assured, and additional destruction serves primarily to hasten surrender rather than alter strategic outcomes. The surrender of Japan on August 15, 1945, ended any further need for Tallboy operations in the Pacific Theater. The total number of Tallboys employed against Japanese targets remained small, fewer than 40 weapons across all missions in Burma and Southeast Asia. Yet the psychological and tactical impact of these limited strikes significantly exceeded what the small number of weapons employed would suggest. Japanese military planners post-war acknowledged that the appearance of weapons capable of collapsing their strongest fortifications had fundamentally undermined confidence in bunker defense as a viable tactical approach. The knowledge that concrete walls 12 feet thick could be reduced to rubble by bombs that attacked from underground created fear and uncertainty that affected decision-making at all levels of command. Positions that should have been held were abandoned. Garrisons that should have fought to the last man requested permission to withdraw. The certainty that had characterized Japanese defensive doctrine, the conviction that fortified positions could allow outnumbered forces to inflict disproportionate casualties on attackers, eroded when the Tallboys demonstrated that no thickness of concrete guaranteed protection. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.